Large language models can explain how to make coffee, fold laundry, or assemble furniture. Ask them to do it in your kitchen and they fail instantly. Embodied AI studies intelligence that grows through physical interaction, touching objects, navigating rooms, recovering from mistakes, and learning what actions actually work. The body is not packaging for a brain. It is part of the computation that makes general behavior possible. The gap between describing a task and executing it is where embodied research lies. Text models learn statistical patterns in language. Embodied agents learn patterns in sensation, action, and consequence. A paragraph about slippery floors does not teach balance. Reading about mug handles does not teach grasp forces. Embodied systems ground symbols in sensorimotor experience, so words like heavy, behind, and full refer to measurable states. That grounding is what lets an agent generalize across new objects and layouts instead of hallucinating confident nonsense. Grounding also reduces hallucinated object references that plague disembodied planners. Embodied agents live in a continuous loop. Perception estimates the state of the body and environment. Action changes that state. New perception reveals whether the action succeeded. This loop runs far faster than language reasoning. A stumble correction happens in milliseconds. A conversational plan unfolds over seconds. Effective embodied systems couple fast reactive control with slower deliberation, each updating the other instead of competing. Reactive layers handle balance and collision avoidance, while deliberation chooses subgoals. Feedback tells the agent what worked. Memory stores trajectories, failures, and context so tomorrow's breakfast task starts smarter than today's. Episodic memory recalls specific events. The drawer stuck yesterday. Semantic memory generalizes. Mugs are usually on shelves. Procedural memory captures skills, how to whisk eggs. Embodied memory is inherently spatial and temporal. It must survive viewpoint change, partial observability, and tasks that unfold over minutes or hours. Forgetting and consolidation trade-offs mirror human learning when homes change layouts seasonally. An embodied agent is never alone. Gravity, friction, human partners, and tool affordances define what behaviors are even possible. Structured labs teach basics. Messy homes teach robustness. Curriculum design matters. Learn pick and place before full table setting. Multi-room tasks force navigation plus manipulation plus social awareness. The environment is not background scenery. It is the teacher that rewards clever actions and punishes sloppy ones with broken dishes. Social environments add norms, cues, personal space, and turn-taking around shared tools. Passive cameras miss what is occluded. Embodied agents actively choose viewpoints, lean to peek inside a cabinet, orbit an object to resolve shape, or lift a box slightly to read the label underneath. Active perception couples planning with sensing. The question is not only what do I see, but where should I look next to reduce uncertainty? Exploration becomes a deliberate skill, not an accident of motion. Information gain metrics formalize which next motion most reduces map or object uncertainty. Affordances describe action possibilities. A chair affords sitting, a knob affords twisting, a button affords pushing. Embodied AI must infer affordances from appearance, material cues, and prior interaction. A language model may say turn the knob. An embodied agent must recognize which surface is the knob, approach without collision, and apply torque with the right hand shape. Affordance reasoning bridges perception and motor control in a single representation. Tool use extends affordances to composed actions. The screwdriver affords turning only when grasped correctly. When a mug slides behind a cereal box, it still exists. Embodied agents maintain object beliefs through occlusion, tracking identity across viewpoints and time. Failure looks like surprise when the hand reaches empty air. Children learn permanence early. Robots must encode it in trackers, memory maps, and prediction models. Long-horizon tasks depend on stable object identity. The egg you cracked is the same egg now in the bowl. Particle filters and track graphs implement permanence when detections disappear behind occluders. Spatial reasoning goes beyond coordinates. It encodes relations. The bread is on the counter, the knife is in the drawer, the milk is behind the door. Manipulation plans depend on these relations to order actions correctly. Language instructions map to spatial goals. Put the plate to the left of the cup. Embodied systems ground those phrases in measurable transforms, collision checks, and human-centric frames like facing the table. Egocentric versus allocentric frames must convert cleanly for mobile manipulators. Prepare breakfast sounds simple until a robot tries it. Locate eggs, fridge, pan, and plate. Open containers without spill. Manage heat safely. Sequence parallel subtasks. Toast while coffee brews. Recover if the bread bag is empty. Long Horizon Embodied AI combines task planning, skill libraries, and constant perception updates. One broken step cascades unless the agent monitors progress and replans with what is actually on the counter. Safety monitors watch stove heat, sharp knives, and human proximity throughout long episodes. Modern embodied stacks combine vision language models with control policies. Language specifies intent, vision grounds objects, action models output torques or end effector deltas. The challenge is latency and alignment. A caption about the red mug must refer to the same mug the gripper targets. Training on robot trajectories, human video, and simulation makes representations shared across modalities instead of 3 disconnected modules arguing at runtime. Action tokenization bridges continuous control with language model planning horizons. Real-world embodied data is expensive and slow to collect. Simulation generates diverse scenes, objects, and failures at scale. Domain randomization varies textures, lighting, and dynamics so policies survive transfer. Yet SIM never captures every contact nuance. Embodied research loops SIM pre-training, real fine-tuning, and continuous logging and deployment. The goal is sample efficiency, fewer broken plates on the path to competence. Real-world reset cost makes SIM the primary source of diverse failure examples. Embodied AI is how we move from narrow automation to agents that adapt in homes, hospitals, and disaster sites. It forces AI to handle partial information, irreversible actions, and human proximity. Benchmarks like household tasks, dexterous manipulation suites, and navigation challenges make progress measurable. The field connects robotics, cognitive science, and machine learning because intelligence without grounding fails the moment a door is heavier than expected. Embodied benchmarks expose brittleness that text-only leaderboards never reveal. Embodied AI still struggles with rare objects, social nuance, and long-tail failures. Data diversity lags language corpora by orders of magnitude. Safety requires conservative behavior around humans and sharp tools. Common sense remains brittle. A robot may know what a stove is yet lack caution about wet floors. Evaluation must stress real homes, not only curated demos. Progress is real, but embodied competence is earned in contact hours, not parameter counts alone. Privacy and consent matter when home robots collect continuous egocentric video. The North Star is agents that assist without constant supervision, tidy alongside you, fetch for elderly residents, or learn a new appliance from one demonstration. Shared autonomy blends human judgment with robot stamina. Personalization adapts to your kitchen layout and preferences. Embodied AI makes technology leave the screen and share our physical context, which is where most of human life actually happens. Regulation and user trust will gate deployment as much as model accuracy. Embodied AI treats intelligence as something developed by acting in the world. Perception, action, feedback, memory, and environment form a closed loop richer than text alone. Active perception, affordances, object permanence, and spatial reasoning connect language to motion. Long-horizon tasks like breakfast reveal why grounding matters. Researchers pursue embodied agents because real environments demand adaptation, safety, and experience. The future of physical AI is not disembodied answers, it is competent presence in the spaces we live. Embodied competence means closing loops in real space, not exporting longer explanations.